Okay. Okay, so so hopefully, did anybody get an email from the TA yet? So doesn't sound like it. Okay, so hopefully we'll try and make that happen. I'll send out something to him today. I have talked with the TA for this course, and hopefully we'll get him fired up. And so what I want him to do is just to work through the homework problems. And let's see, I haven't actually looked to see if did anybody look to see if the homework, if the appendix was restored? Let me just double check that. So 1 second here to do that.
It is not restored on mine.
Okay. Yeah, I'll look real quick here. I would think they'll get it done today. It's they actually they went overboard. Actually, they implemented it as a test, which I didn't really want them to do. I just wanted to put the list of problems in the appendix. Okay, let's see. Let me log on here real quick. Shouldn't take but 1 second to do that. And then make sure I get the right session. Let's see. Here. Yeah, it's so I can still see it, but it's not changed yet. So okay, so hopefully they'll get that done quickly this week. All right. So let me. Okay, and then let's see this. Okay, I'll share my screen again. Okay, so we'll hopefully get that going. The end of chapter quiz is for chapter 3 is due on Wednesday. So I'll probably take a look at that on Wednesday and just go over a few of the questions so you kind of are oriented on that. And then the chapter 4 quiz will be due on the 7th. So that'll be next Monday. And we'll be in person on the 7th. I think that's correct. All right. So make sure you read through chapter 3 and you can look at the slides. All right. So let me, so let's bring this up. Okay. Can everybody see that, hopefully?
Yes, sir.
All righty. So what I want you to get out of chapter 3, so I want you to be able to understand why our digital design tools are based on the binary system. And why is that? And of course, that's because all the devices that we use, for the most part, are devices that have 2 states: true, false, 0, 1, usually represented by logic levels of ground and traditionally 5 volts, but these days that number is going down for many systems: 3 volts, 3.3 volts, 1.8 volts, even some chips now running below a volt. So so the actual voltage level that's correlated with 1 and 0 has changed, or is changing, and continues to change. But the idea that we have 2 states, and a lot of this is driven by the fact that our transistor switches that we use in most of our integrated circuits are used as two-state devices. We push them completely into cutoff, or we push them fully into saturation so they're fully on. And we don't really run them in between. Now, if you're making a transistor amplifier, that's a little different. Then you would use it in the in-between part where it has a mostly close to linear operating range, and that gives us some linear amplification of signals. And of course, we do use in the analog world, we still use transistors in that manner. But in the digital world, we don't. We only use them fully turned on, fully turned off. That's it. I want you to be able to write all the 2 input truth tables for the major gates, and or exclusive or, and then NOR and NAND. And then this is probably the most important thing. You need to be able to take a truth table and write down a 2-layer network of AND gates and OR gates with obviously inverters potentially, and implement it with either the AND gates as the input layer and 1 output OR gate, or the OR gates as an input layer and 1 output AND gate. And as we go through some of the rest of the first 2 parts of the course, one of the things we'll do is work on how you optimize that so you can get it the simplest possible network that you can have, and what some of the other networks are. We've already teased that a little bit. Like, for instance, we can implement it in with NAND, with an input layer of NAND gates and 1 output NAND gate. We can implement it with an input layer of NOR gates and 1 output NOR gate. And we showed how to do that with the alternate symbols. And then we want to be able to describe at least 3 sets of complete gates. And we've talked about that on Friday, which has to do with AND or AND, or NAND, or NOR. So those are the classic ones. And for fabricating integrated circuits, for the most part these days, we use either NOR or NAND sets of gates for our networks. Okay, so there are some advantages of our 2-valued logic. One is we have all this intellectual property out there that's already been done, a lot of which is in the public domain, so it's free. And most things have been already coded up in our hardware description languages. So for standard building blocks like math coprocessors and a whole bunch of things, you can just license the IP. There are a wealth of tools for using developing logic design based on our 2-valued logic. And then, of course, there are a wealth of existing designs that can be enhanced, taken to the next level by just making some improvements. And of course, that's how we've gotten the complicated devices we have. The early efforts to develop computing machines were vastly inferior to what we have now. But we couldn't have what we had now if we hadn't developed those things way back when, and built on the skills and logic and knowledge we gained doing that. So a lot of our work is built on these existing designs, and it's all done in 2-valued logic. And then finally, we have pretty solid theory that undergirds all this, which is what we learn in this course. So there are lots of advantages of 2-valued logic, but there are some downsides. For one thing, things are either true or false in our 2-valued logic world. Now, obviously, you can use 2-valued logic to do all sorts of interesting things, including having conditions that are undeterminate, kind of in the maybe world. But it's not it's not a natural phenomena of 2-valued logic to have maybe. Maybe with 3-valued logic, that would be sort of, we would think of it true, false, and maybe. And that would really change our whole way of thinking about logic design. That would be a fundamental transition, and maybe that'll happen someday. I don't know. The other thing that may be a downside that's already, where we're already pushing the limits, and that is in our memory cells, particularly flash. Flash already uses tri-state and quad state devices because they get much better density in the storage. So there are places where we have departed from our two-value world, and that inherently the push comes there in the storage medium, because obviously if you can put essentially 2 bits in a storage location instead of 1 bit, the same location, you've just doubled your density. So, and that's one of the reasons why that's happened in the flash memory world. Okay, so we talk about Huntington's postulates. I guess this is pure theory, but these are sort of foundational to our way of thinking about logic design, even though I had done an awful lot of logic design work before I ever actually saw Huntington's postulates. So you don't have to know these necessarily to be guided by them at some level. Anyway, closure. Any operation must give a result of true or false. So there is no maybe in our two-state logic world. Now we can construct, with very complicated logic, we can construct maybes, but it's absolutely maybe or absolutely not maybe. So every operation has to resolve at the binary level, at the fundamental logic level, to true or false. And then we have these identities where if we OR X with 0, we get X. If we AND it with 0, we get 0. If we OR it with 1, we get 1. If we AND it with 1, we get X. And then this commutative where X ORed with Y is the same as Y ORed with X, and X ANDed with Y is the same as Y ANDed with X. We don't put the little multiplication sign in here. Remember, we are using addition to represent OR. We're using multiplication to represent AND, but this has nothing to do with addition. This has nothing to do with multiplication. These are just notations. And that's one of the things you have to sort of get out of your mind, is that this idea of plus has anything to do with adding, and this idea of multiplication has anything to do with actually multiplying. Now, at some level, it kind of works. If you multiply anything by 0, you get 0. If you add 0 to anything, you still get what you had. But there is no such thing as subtraction in our digital world. There's no such thing as division when it comes to these logic operations here. So just think of this plus and this time sign as OR and nothing else. And then you can group them. This works fine for OR gates and AND gates. It doesn't work for NOR gates and NAND gates. And then we have complementation, where X ORed with its complement is always 1, and X ANDed with its complement is always 0. And then this idea that 0 can never equal 1. They are distinct and they can never be the same. All right, just some guiding thoughts there. All right, so here's a chart of all the different 2-input logic functions you could have. All right, so we have an input A and an input B, and then that gives us a truth table with 4 rows because we have 2 independent variables. So n is 2, 2 to the n is 4, so we have 4 rows, 1, 2, 3, 4. And of course, the first row, A is 0, B is 0. The next row, A is 0, B is 1, A is 1, B is 0, and then they're both 1. And here are it turns out there's 16 ways you can describe F, right? You can have them all zeros, you can have them all ones, and everything in between. And if you do this, then you can identify some patterns which are extremely interesting and important, and some which aren't particularly interesting or important. Obviously, all zeros, not particularly interesting or important. All ones, not particularly interesting or important. But this particular combination here, where the desired output for F is 0, 0, 0, and then for if they're both 1, 1, that defines the AND function. And then here's some other ones. This is just A ANDed with not B. And this is, so this just changes, this basically makes what the 1, 0, the actual AND result, because we're using B prime. This is just equal to A, and this is not A, B, so that's A prime ANDed with B. This is just B. This is the exclusive OR function. This is the inclusive OR function. And of course, these two are very important. And then here's your NOR, and here's your exclusive NOR, and over here is your NAND. And then we have B prime, and then A ORed with B prime, A prime ORed with B. So of all these 16 possible functions, the ones that are really important that have great utility in our logic world are this AND function here, this exclusive OR, inclusive OR, this NOR, exclusive NOR, and NAND functions. So we have what, 1, 2, 3, 4, 5, 6 really meaningful 2-input functions. Now, if we did this same table with 3-input logic functions, then we, instead of 16 choices here, we would double that, right? We'd have 32, and or maybe even more than that. But that what we mostly do is we just extend these 6 important functions to the 3-input and 4-input and 5-input logic functions, and we don't really bring on board any really in any of the potentially unique functions with 3 inputs that you could possibly have, and that's sort of an interesting phenomena. So something to think about. All right. So codes, we've talked about this quite a bit. And so we have codes to represent numerical values. And normally, almost exclusively in the digital world, we just use the binary representation. That's certainly true for integers. When we deal with floating point, then we do it a little bit differently. And we use the IEEE standard for floating point numbers, 754, and it did just change 2 years ago. They added some new representations. For unsigned numbers, then we just use the absolute binary values. For signed numbers, we use 2's complement, and that's pretty universal. And again, for floating point, we use the IEEE standard. For letters, we have a number of different codes. For many, many years, all we really had, we had ASCII with a few other competing representations. But in the last, I don't know what, 30 years, there's been a tremendous push to incorporate other character sets. And I'll talk about that in just a second. And now we finally have Unicode, which covers every script, both ones that are ancient and dead and not used anymore, and all known scripts that are being used. Doesn't necessarily, the scripts don't always translate directly into languages, because there are some languages that can be represented in multiple scripts, which is kind of crazy. We have codes for printing. We normally call those fonts, and there's a zillion of those. I remember there was a time in the evolution of the computing world where everybody was just crazy over fonts, and new fonts would come out and people would be excited about them, and people were always getting as many fonts as they could, and they were then typing documents and then changing the font to make them look cool. And this was just something that we could never do before. It was a brand new thing, and people just went crazy with it. For most of, for you guys in this class, this is old hat. You've been dealing with fonts ever since you were born, and you're not impressed with that at all. But I can certainly remember where seeing a scripting, a font that looked like handwriting for the first time was just mind blowing to me. All right. Well, anyway, and then we have a number of different codes for representing pictures, a number of different codes for encoding video. And this video world is really crazy. We're sort of at the point now where we're now using, there are now, so my son-in-law actually does film, and he's out in Hollywood, works for Fox. And so he's kind of deeply embedded in this world. And what's interesting, they are now using cell phones to take production level broadcast quality video, and they're actually making content with just cell phone videos. They could use cameras. They're just choosing to use the cell phones instead because it's easier and more convenient. And they can get 4K quality off the cell phones, and that's really all they need. And then they just process it and crunch it into whatever they want. There still are cameras that take video better than that. And then what they do, they have it in a native format. Like there's a camera format called RED, and then they basically crunch it down into whatever format they want. And for some real high-end things, you still need to do that, like for the 3D surround video. I forget what you call it. There's one downtown, the Video Max or something, where you can see this, get this, crazy video effect. And also, of course, then we have three-dimensional. We have the 3D video. And then we have a lot of other codes that are error correcting, codes, gray codes that only change by 1 bit from each representation, and things like that. All right, so ASCII is the big one, and it's cranked up in 1963. So you can see it's been around a really long time, and it's basically 7 bits. So there's 128 characters. There is an expansion of that, ANSI, which actually is 8 bits and has some more characters, but basically, as an English, using an English language or a language with basically using the Latin alphabetic characters, Latin script, you can represent most things. What's left out of ASCII is accents on some of the characters that you see, obviously in some Spanish text, of course, and also things like Greek letters, Russian letters, things like that are missing. And of course, none of the Asian alphabet scripts are involved at all. This is still used a lot, and it's still part of even Unicode, like the UTF-8 code. If you want to represent just the standard characters and symbols that are shown in ASCII, then you just need the first byte of the UTF-8 code. But now Unicode basically covers everything, and there are Unicodes for all known character scripts. Now that doesn't necessarily mean every language, but that's the idea. And obviously these things are so there's still a lot of machine dependent issues that, like when I taught a course in China in the summer of 19, and in Shanghai for a month, and seeing our Chinese students text was pretty amazing, because when they text in the in the symbols, in China, in Japan they call them kanji, but in China there's a different word. I don't remember what it was, But those symbols, how do you do that on your cell phone? And there's actually two different ways to do it, and they showed me both ways. Still didn't make much sense to me because I don't understand those, but it's pretty cool. And so you can definitely do that. But obviously for keyboards, it's also kind of a little bit challenging. And anyway, so all sorts of interesting things. Lots of work still to be done for everybody in every place in the world in their own language to be able to have their cell phone speak their language in a fairly convenient way. Okay, we've been over these alternate symbols a couple of times. What I want you to remember is that this is what we're showing here, right? The AND gate looks like this. The OR gate looks like this. The NAND gate is an AND gate, but with a tick mark on the parentheses so that the output is inverted. And then the same with the NOR gate. It's the OR gate with the output with a tick on the parentheses so the output is inverted. We'll come back and use these when we use algebra to do these transitions. Okay, so we already, on Friday, we did talk about functionally complete sets of gates. So any logic expression can be implemented in two layers with a set of AND gates, OR gates, and inverters, or with just NAND gates, or with just NOR gates. And actually, there are other functionally complete sets of gates as well. But for the most part, we don't use those that much, hardly at all. Okay. The one maybe exception here would be exclusive OR gates. We do use those, but those are much more complicated to make than NAND gates and NOR gates in an integrated circuit. So when we make an integrated circuit, we're normally making NANDs and NORs. Or, well, one or the other. We're not making both on the same chip typically. Okay. So basic logic operations. So these we're gonna stick with AND and OR for a while now, and obviously we're going to use inversion, but we're gonna be sort of pretty free with inversion. We're just going to add a tick mark if we need to indicate the inversion, or a bubble. We're not gonna put necessarily the actual. We're not going to draw the inverter in the circuit, and we can implement any logic expression in two layers with these basic operators. Okay, so, and we've kind of defined these already. We'll just go through them again. Obviously, in inversion, you put in an X, you get out an X prime. That didn't show up real well. We also call it a NOT. And usually the logic 1 is represented by high voltage and logic 0 by low voltage. But they're really true and false. They're not really the values of 0 and 1. Here's the AND. You could put a dot in here. And let's see, you can put a dot in there to represent addition, and you can put a plus to represent, to represent ANDing, and you can put a plus to represent ORing, but we don't normally include those symbols in the gates. And I kind of left that one in there and didn't mean to. All right, so for the AND gate, you should absolutely know this truth table. It's easy to remember it. You just know that it always outputs a 0 unless both inputs are 1. And for the OR gate, it outputs a 0 if both inputs are 0. Otherwise, it outputs a 1 if any inputs are 1, or if they're both 1s. Okay, so those are the gates. We've already talked about truth tables, and I talked about those at some length on Friday. And now I'm going to transition and talk about these a little bit more. So a truth table is just a list of the desired outputs for each input pattern. And of course, you have if you have n independent variables for your input, then you have 2 to n rows to describe all possible combinations, and you have to specify the desired output for each row. Now, there are times when there are some rows that we know will never occur, and therefore we don't usually we don't have to specify an output. We can leave it as what's called a don't care, so that we can choose whatever works, whatever makes our logic simpler in the end. And that's where the don't cares come in. It's when It's when there are input patterns that will never occur. This truth table is really basically the gold standard when you do your design. So once you get your truth table established, then you can go ahead and do your design. And as long as your design implements your truth table faithfully, you're good. The only problem is if your truth table's wrong, then your gold standard's wrong and everything's screwed up. It's kind of like I don't know if you guys know the story of the Hubble telescope, but when they sent it into space, they to their shock, horror, and utter embarrassment, they realized it was out of focus. And when they went back and tried to figure out what in the hell happened, they realized that when they made the mirror, because it's a reflector, when they made the mirror, they had a little gauge that a precisely machined gauge